So, gravity. Yeah, gravity. Gravity. Yep, gravity. Well, anyways, what if gravity isn't actually the way that gravity works? General relativity gravity. Capital gravity. What if that's not how it works? What if it's not the amount of mass in an area defining the gravitational thing emitted from that area, as well as its gravitational attraction to another area? So let's get into it. Just pull up the script here. This is episode 1 and all, so give me a little credit here. Doesn't that kind of look like the word Joe? Isn't that funny? But anyways, one second. In this video, I'll be explaining my new theory of physics. Well, that makes it sound more than it is in my opinion. And the title of the paper that I'm trying to publish currently is vacuum space as the cause of gravity. A creation of vacuum space from mass to energy conversion. That's the idea. The title could be called anything. And the specifics, well, it'll depend on the evidence of what the title will be. But let's get into it. Wow. Intro, just imagine there's a little intro cutscene there. But anyways, the basic idea is that matter, under certain conditions, decays into energy. Pretty standard stuff. Energy released is equal to matter lost. I'd like to say matter specifically and not mass. Although in some systems, the gravitational potential could be lessened by matter converting into energy, because now there's less matter pushing on the center to create a release of energy, or conversion to energy. It doesn't necessarily need to be released. But anyways, let's get back to it. It was a little side tangent, I suppose. So yeah, matter under certain conditions decays into energy. This decay processes. This decay process creates gravitational effect. That's a new part right there. And regular physics, as we see it currently, nothing new being added, you would say that mass does indeed deconstruct into energy, aka light, and maybe other things. Who's to say? And the amount of energy gains in the total system, absorbed into things, released into the environment, to be absorbed into other things further away. It is proportionate to the amount of matter that has been lost. So fundamentally, some amount of matter has some amount of energy that it can be equated to and even converted into. But anyways, let's just read the whole script. Let's read the whole script just for fun. The basic idea is that matter, under certain conditions, decays into energy. This decay process creates a gravitational effect. That means gravity isn't caused by matter itself, but rather when matter is in a state that allows it to convert into energy. I don't like how I read that, but gravity isn't caused by matter itself, but rather when matter is in a state that allows it to convert into energy, it causes gravity. I like to add that at the end. It sounds a bit better. Furthermore, the gravitational strength of a region depends on how much mass is. I don't like that. Fucking, I had AI write this. They fucking rewrote my words, said I'd make them sound better. I don't like that. I'm going to say it my way. Furthermore, the gravitational strength of a region depends on how much matter is being converted into energy over a given time interval. Fair to say. That's the idea. This is a new idea. In Einstein's curvature of spacetime, there's a curvature of spacetime caused, and there's a lot of matter in a particular place. This causes a gravitational effect. In my version of physics, there is a gravitational effect caused by the deconstruction of mass to energy. Given an enormous amount of matter being in one region, there would be an enormous amount of pressure placed on the center. This center would then start converting matter to energy, creating a gravitational effect that draws in more matter. In Einstein's version, the more you have of it in one place, the more gravitational effect is emitting from it, without necessarily needing the conversion to take place, or it to be equal to the conversion rate caused by the material in the area. And I say, how in the fuck do you get gravity from nothing? Why would it just pop up out of nowhere? Why would it be a constant state of things? I don't think so. I think it's matter converting to energy that then has a subsequent process to it. Like say something converts matter to energy. Well, it does this by releasing light. That's how the matter converts to energy. So it's releasing itself by breaking itself apart into these very high speed particles that spread apart in all directions from the place where this is happening. And so, since there's this bubble that contains all these bits of light, and they're all doing that, there's this vacuum that would form as a result of this, and it would want to dissipate in all directions as well. And so that's what I think gravity is. Essentially, it's a counter reaction of light leaving an object. So that's the idea, really. And so we'll get into it, though. And I don't think mine is proven. I don't think Einstein's is proven. And I think that there's a hole in the way Einstein views, in his papers, the gravity. And, well, there's some anomalies. Currently, where on the surface of the Earth, there's denser material in an area comparative to the other areas in a layer called the mantle, And under those dense layers, the denser parts of the layer, there's denser here, less dense over here, less dense over here, so on. The denser part, you would expect that if you would expect that if mass were the cause of gravity, just it being there, my bad. You would imagine that if matter, just the cause of it being there, were to cause gravity, then a zone of the Earth where it has this dense mantle, it would cause a stronger gravitational effect. And especially if you were to take, this object's, here's where you're standing, here's the area where the gravity discrepancy is. Here's the slice all the way down to the center. If there's a higher density of material in this area, then you would expect there to be a higher gravity in that area on the surface, caused by the more matter in that area having a higher mass, because the area has higher matter, it has a higher mass, simple, more gravity. But in actuality, the opposite happens. When there's denser material here, in that zone, there's lesser gravity on the top. And I would expect that to be a trend that continues. People aren't even in agreement that it continues, which I find cool. So I get to be the first person to say that. I think that's really strong, and that's really the basis of the paper's evidence at this point, is that that pattern will continue, and there will be other zones like this where there's higher density material under the area on the surface of the Earth, under the surface of the Earth in that area. It's higher density of material. And there's a lower gravity than places that have a lesser, denser material. And then I go further into that. That's pretty apparent. I think we'll find that pretty soon. My paper predicts a gravitational anomaly in the Antarctic, where there is currently density information of what's underneath, but not gravitational information. So I think when they find that, if what I'm seeing is right, if they really didn't collect it yet and it really is like that, that's kind of perfect. I think they will find that there's a lesser gravity in those areas that are defined in the paper. So I predicted a gravity discrepancy, where standard physics wouldn't be able to predict it. My model does predict it and continues to predict it. But that's all it is. It's just a thought experiment. One versus the other. Imagine it this way, imagine it that way. Well, here's my math to my imagination. Here's the math to this imagination. My math works better. But, But anyways, I think there's more to it. If this is seen to be true, then there are other things that would really prove it, yeah, cool. Okay, so let's get back into the thing here. I'll just reread the last sentence that we left off on. That means that gravity isn't caused by matter itself, but rather when matter is in a state that allows it to convert to energy. Furthermore, the gravitational strength of a region depends on how much mass is being converted to energy over a given time interval. Since this is a propagating effect, different materials with different permeability to vacuum emissions will cause gravitational variations, even at equivalent distances from the energy conversion source. Like we talked about with the mantle and the core of the Earth being the cause of its gravity, because it's the cause of it's the energy convergence point at the center. Um, so the idea that I had with it was that if something has a higher density, then it absorbs more light. If you were to shine a flashlight through, say, my hand versus a rock, more gets through my hand. My hand is less dense. So seeing gravity as a counter reaction or equivalent reaction of gravity. Gravity to be an equivalent reaction or part of the process of light emission. You would then expect the gravity to similarly have a propagation rate through the material that is less of it gets through denser material. So there would be lesser gravity left over on this side once the gravity goes through, just like how there's less light coming through. And that should be dependent on the density rate, or density amount. But anyways, back into it. Okay, like we said. Furthermore, the gravitational strength of a region depends on how much mass is being converted to energy over a given interval. Since this is a propagating effect, different materials with different permeability to vacuum emissions will cause gravitational variations, even at equivalent distances from the energy convergence source. So, for more advanced gravitational predictions, more mass decaying into energy in a region, the more mass decaying into energy in a region, the stronger the gravitational effect. It emits, I would say. It also is emitted from the paper here. So, yeah, it emits. I'd like to add at the end of that sentence. The objects nearby are pulled towards this region due to the vacuum space that's released. Denser objects have more material per unit of value and therefore absorb more light. They're also affected more by vacuum space, meaning they are pulled more strongly by gravity. So we didn't go over that. They're pulled more strongly by gravity because there's more of them. So if you have this light casting effect that's going over an area, imagine you have like a not so dense gas. So you have 5 particles here on this line versus you have 250 particles here on this line. And then you have your casting effect, which gets less dense the further away it is. So we have 750 that hit this line of 250. So now there's 3 per, but versus there's 500, there's 50 or whatever per unit here. So each individual one would be less, but I'd expect the absorbency rate to be more. So overall, it would get pulled in greater, which is also an observed thing. Yeah. So I think that makes inherent sense. Denser objects have more material per unit volume and therefore absorb more light. They're also affected more by vacuum space, meaning they're pulled more strongly by gravity. This leads to specific predictions. If a part of Earth's mantle is denser than the surrounding material, yet located farther from the center of the Earth, it will be more gravitationally attracted toward the center. However, because it absorbs more vacuum space, the surface area above it experiences a lower gravitational pull. And I think it's sort of unnecessary to say that it's a further distance from the other comparable thing. Because in the case we observe it, in the case we're using in the paper, it's not. And I mean, it would depend upon if the density were to be proportionately more when you get to further distances. So it actually makes it a lot more complicated and doesn't make it inherently true that something with a higher density would have that effect unless it was a reasonably more so higher density. Uh, Because it absorbs more vacuum space, the surface area above experiences a lower gravitational pull. Okay, that's where we were at. In traditional physics, if mass were defined strictly by the amount of matter in its given space, we would expect the surface above a dense material to feel more gravity, not less. True. I mean, unless it were to be like a counter reaction, like, so the dense here, the dense thing on like the mantle layer causes like a gravitational effect. It's pulling in both directions. So it's pulling the person on the top down. But it's also pulling towards the center more. And the center's pulling on it. And somehow this causes like a not pulling together effect. Because there's like more going this way than another region has. And there isn't too much of a big effect. And there's like a lesser effect than is currently believed to be for how dense an object needs to be to have a certain. So I think that's inherently already wrong, but I don't know. See, it really does point to it really can't be. I don't see a reason how, given what I see the paper written here, I don't see that there's a reason that it could actually be mass. Like the amount of matter in an area causes gravity. Although in a lot of cases, it's really not that far from the truth. The amount of matter in an area being closely proportionate to the amount of gravity that area emits due to the pressure caused by that amount of matter in an area, causing a mass to energy conversion. But it's the mass to energy conversion that does it. The discrepancies are here shown in this paper and the words I've said previously, and the words I'll say after this. Um, so, in traditional physics, if mass were defined strictly by the amount, and it is, by the amount of, it's sort of, I mean, it is, right? It pretty much is. I don't know, it is. In traditional physics, if mass were defined strictly by the amount of matter in a given space, we would expect the surface above a dense material to feel more gravity, not less, but current geoid anomaly data contradicts this. In fact, areas with denser subsurface structures often have less surface gravity, lending to the credibility of the vacuum emission model. My model. Based on this alone, we can predict that there will be lower gravitational readings in certain Arctic regions where we talked about that, yeah, where high density material blocks vacuum emissions from the Earth's core. This is exactly what my this is yeah I already sort of said that. This is exactly what my gravitational paper predicts. Well, it doesn't conclusively prove that gravity arises from matter to energy conversions. It does challenge the conventional view that gravity is simply proportionate to mass, well, matter in a present region. I should say matter in a present region. As suggested by general relativity, space-time curvature model, and similar theories. Further research and testing will be necessary to determine whether matter to energy conversion is the primary cause of gravitational force. Well, let's see. Mass. Let's talk about mass for a minute. So mass is defined as the amount of matter in something's area, say this area, the amount of stuff in it, the amount of particles overall, or particles basic pieces, then determines its gravitational effect that it emits. And therefore, that is the definition of mass. So the definition of mass already presumes the relationship between matter and gravitational effects. Matter in a zone equals gravitational effects. So you can't say that accurately, you can't say that the amount of mass in an area doesn't determine the amount of gravity emitted. So, if it were to be proven that, because the definition includes that right? I think it does, yeah. We looked that up, but yeah. So, anyways, if if it were to be seen as true that mass to energy conversion causes gravity, then the definition of mass would no longer work. Mass, the term, would cease to be. How about that? I mean, let's really check though. I don't want to say something really stupid. We'll check right now. This is near the end of the video, but we're just doing this as a little ending. Mass definition. Mass is the quantity of matter in an object, measured in kilograms. It's an intrinsic property of a body determined by its atomic and molecular makeup. Mass is different from weight, which is the force of gravity on an object. Mass remains constant, but weight can change depending on gravity. So, it says in the definition, like we just read there, that Mass remains constant, but weight can change depending on gravity. In physics, mass is a fundamental property of matter and is measured by a